Hello and welcome to the 14th lecture of the course Basics of Semiconductor Devices and Technology. So far we talked about various aspects of semiconductors all the way down to electrostatics of p-n junctions or p-n junction in thermal equilibrium. And then we talked about how these p-n junctions behave under reverse bias condition. Now, if you have to talk about the transport through the p-n junction, or let's say p-n junction diode, we need to consider how p-n junctions behave under the forward bias condition, and to understand the transport we need to derive a current voltage relationship. So what will happen if we apply a forward bias? If we apply forward bias, the potential barrier will come down. So we remember that earlier there was a potential barrier. If I can just draw the conduction band energy level, this is N side, this is P side, and if it is N side we have these free electrons present in the conduction band, and there is a barrier which we called built-in potential or VBI, QVBI. If we to put in the electron volt terms, there is a barrier which is protecting or blocking these electrons to move to the other side, right? So this barrier need to come down. So what will happen if we apply a forward bias? This barrier, which is QVBI, will reduce from QVBI to Q times VBI minus the applied forward bias. Let's say the applied forward bias is VA. So as the barrier lowers, this potential well, or the step, this will come down. As we increase this, so this part will go up, the barrier difference will get reduced, and this is what is going to basically allow the carrier flow or enhance the carrier flow from N side to the P side, and the similar thing happens from the P side to the N side. Now, what is important to note that in this case, in diodes, the current transport happens because of the minority carriers. These electrons have to move to the P side. These holes here have at the P side need to move to the N side. So when these electrons move to the P side, these electrons at the P side are the minority carriers, minority excess carriers. Similarly, these holes at the P side, when they move to N side, these holes at the N side will be minority holes or excess minority holes at the N side. And then these excess minority carriers are subject to minority carrier drift, diffusion, or the recombination process. So, to understand further, if you can see this picture, what it shows, as we have seen in the previous module as well, the holes which are present at the P side, these are the majority carriers, they diffuse to the N side. Similarly, the electrons which are present at the N side, they diffuse to the P side. So as these holes diffuse to the N side, they become excess minority carriers, and as these electrons diffuse to the P side, they become excess minority carriers, right? So these holes diffused to the N side are excess minority holes, and these electrons diffused to the p side are excess minority electrons. They are called, the holes are called minority at the n side because the majority is n. So any disturbance in the minority carrier concentration is the excess minority carrier concentration. And what are these excess minority carrier concentration? These are holes. Similarly, these electrons, when they diffuse to the p side, they will disturb the minority carrier concentration, or which are electrons at the p side, and therefore they are called excess minority carrier or excess minority carrier concentration. Now let's see how the band diagram will be affected. This is something which is under equilibrium. This is what we saw in the previous module. The difference between the conduction band at the p side and the n side is the built-in potential. We derived a relation for that. We also saw what happens when you apply a reverse bias. So basically the built-in potential was increased when we apply a reverse bias, and the built-in potential was increased by a factor of VR, where VR is the applied reverse bias, right? Now similarly, if we apply a forward bias, so if you see the difference between these two, the polarities are reversed compared to the reverse bias. So the polarity are reversed means you can call this, if you put in this equation, right, if it was plus VR, in the other case it will be minus VA, where VA is the applied voltage, right? So when it's reverse bias, we add with built-in. When it is forward bias, we subtract with the built-in potential, because the height or the barrier between the conduction band at the p side and the conduction band at the n side is going to reduce. So this barrier, since this is getting reduced, this is getting lowered than VBI, the total barrier becomes VBI minus VA times charge in electron volts. Now in both the cases, remember that the Fermi energy level converted into quasi-Fermi energy level. So the moment system is under non-equilibrium condition, whether it's reverse bias or forward bias, system is in non-equilibrium condition, and the moment it's in non-equilibrium condition, which means the minority carrier distribution is perturbed, then the Fermi level will no longer be used, and what we will use is the quasi-Fermi energy level, right? So when you apply the forward bias, what happens? The electrons are going to flow from the n side to the p side, and the holes are going to flow from the p side to the n side. And as this barrier is reduced, right, more and more holes are going to flow to the n side, and more electrons are going to flow to the p side, or in other words, more and more electrons are going to diffuse to the p side, and more holes are going to diffuse to the n side. And once they have diffused, on the other side they have created an excess minority carrier, and then these excess minority carriers are subjected to the drift and diffusion kind of transport on the other side. Mostly we will see that it's diffusion transport of these excess minority carriers which contribute to the diode forward current. Okay, so let's see how do we derive a current transport relationship for a PN junction diode, right? What is this current transport relationship? This is nothing but the relationship between the current and the voltage, the diode current and the diode voltage, right? So all of you remember that you have seen this kind of diode characteristic, and on the reverse side you see something like this, right? So how do we derive this relationship? This is voltage, this is current. So how do we derive this kind of relationship, right? So we'll see how do we mathematically derive a relationship which basically gives this, right? So we know this relationship only after the derivation is complete. We don't use this knowledge to derive something. We derive, and from there we see that the relation between the current and voltage is of this form. Okay, So you remember we had taken some assumptions in the previous module for the space charge, for the junction, for the minority carriers, for the diffusion and all, right? The diffusion of majority carriers from one side to the other side. Now we will follow some of those assumptions, and then there are a couple of other assumptions and the procedures that we have to follow to derive this relation. The first assumption is that the abrupt depletion layer scheme, or we assume that the depletion layers are abrupt, though practically we know that they are not abrupt, but here we are assuming that they are abrupt. Okay, the junctions are abrupt, they are uniformly doped, both sides are homogeneous semiconductors, P is uniformly doped, N is uniformly doped, the interface is abrupt, and the junctions are abrupt, and the depletion layer is also abrupt, right? So therefore the space charge region have abrupt boundaries, and outside these boundaries the semiconductor is neutral, so it's charge neutral outside the depletion region. We'll also follow the Maxwell-Boltzmann approximation. So this is basically to all our derivations so far in terms of relationship between the carrier, minority carrier and majority carrier concentration, or majority carrier concentration versus Fermi energy or intrinsic Fermi energy levels, or the relation between majority carrier, minority carrier, built-in potential and all of that followed Maxwell-Boltzmann approximation. So we'll use the same equation, which means the Maxwell-Boltzmann approximation is still applicable. And if it is applicable, which means the relations that we are deriving are basically for non-degenerate semiconductors, right? We will also assume that the low-level injection condition is applied, which means the injection is such that the excess carriers are not going to exceed the majority carrier concentration. So that's the low-level injection condition. Now, if you look into the structure, we will assume that the total current is also constant across the PN structure. So let's say if this is your diode, and this is where the current enters and it exits, and let's say across this from here to here, let's say if this is x equals to 0, this is x equals to x1, from 0 to x1, and the current density across this is J is independent of x. The total J is independent of x, and that's what you see, the total current density J is independent of x, which means it's flat across the entire device, right? The individual electron and hole currents are continuous functions throughout the PN structure, which means that we are assuming that the individual electron and hole concentrations, which are current concentrations, which are Jp and Jn, right, they are continuous. So there is no discontinuity in the current density because of electron flow or the hole flow. We'll also assume that these electron and hole concentrations or current concentrations are uniform and constant throughout the depletion region. So that's what you are assuming here, that inside the depletion region there is no change in the current density, right? Which means that whatever enters from this side, the same hole current exits from this side. Whatever electron current enters from this side, the same electron flux exits from the other side. That's the meaning of the current inside the depletion region being flat or being constant. And then the last assumption is that the sum of individual electron and hole currents at any point is the total current, and that's basically same as what we said in point number 4, that the total current is flat, and the total current will be flat only because the total current is nothing but the electron current plus the hole current. Now the electron current could be a function of x, the hole current could be a function of x, but at any point if you add these two, it should give you a constant current, which means that once we have the Jn as a function of x and Jp as a function of x, we can find these values at one of the point and just add it to find the total current. We don't have to worry at what point we add. Wherever we add, wherever we find their values, we just add and we are done. Now what could be that point? Let's think about it. If the current is uniform inside the space charge region, which means that we can take any value for these two from minus xp to xn and add. It can be, let's say, electron current at minus xp and hole current at plus xn. We take these numbers, we find these numbers or relation for that, we add, we get the total current. Okay, so before we move forward, let's see, there are certain common terms that we should be aware of, right? Now what these common terms are, and I would suggest that most of you, before you proceed, most of you try to memorize these things, because this will help you follow the derivation, because the derivations subsequently are going to consider many of these terms, and many of these terms or notations can be confusing. Therefore it's better if you can just print it out, keep it in front of you, or memorize all these things. It will be easier for you to follow the derivations, right? Many of the things you know very well, like for instance Na, we always use Na as the acceptor concentration in the P region, right? Nd is the donor concentration, and in this case we have N region, so we are considering Nd as the donor concentration in N region and Na as the acceptor concentration in the P region. These regions are not compensated in our assumptions, which means the P region is just doped with acceptor and N region is just doped with donor. So the thermal equilibrium majority carrier electron concentration in the N region is nothing but the doping that we introduce in the N region, which is Nd. Similarly, the thermal equilibrium majority carrier hole concentration in the P region is nothing but the doping that we introduce in the P region, which is Na. But for this, we will not use Na and Nd in our derivations. We will use N, N0. Now here, N, the first N corresponds to the electron concentration. The second N corresponds to N region, and 0 corresponds to thermal equilibrium situation. Similarly, if it is P type, so the first P corresponds to the hole concentration, the second P corresponds to P region, and 0 corresponds to thermal equilibrium. Now when these two are same, if it is NN or PP, we are actually talking about the majority carrier concentrations, which means this is N electrons in N, which means this is majority carrier, holes in P, majority carrier. Now if it is minority carrier concentration, then what we will write? We will write electrons in P in thermal equilibrium and holes in N in thermal equilibrium. So holes in N are minority carrier, electrons in P are minority carrier. 0 will always be used for thermal equilibrium situation. So let's see what is that. And you also know that these two are related, right? So if you know the electrons in N, right, you also know the holes in N. What is the relation? The multiplication of these two should be equals to Ni square, and that takes us to the next one. So the electrons in P is nothing but Ni square by Na. Na is your holes in P under equilibrium. Now holes in N, which are minority carriers in N region, is Ni square by Nd. Nd is electrons in N region under equilibrium, right? Now this was about the equilibrium concentration, which means the system, the forward bias or reverse bias was not applied. Now what if the forward bias is applied? Then this equilibrium is going to be disturbed. Which equilibrium will be disturbed? The minority carrier concentrations are going to be disturbed. The majority carrier will not be affected. The minority carrier concentrations are going to be disturbed because of the diffusion process, start of the diffusion process from the other side, right? So then for that we can say the total minority carrier concentration as NP. So NP becomes the total minority carrier electrons in the p region and total minority carrier holes in the n region. Right? Now, if we say that we want this minority carrier concentration is apparently a function of x, so you can also write this as x, and if we find this value at a given x, let's say np minus xp, this is the electrons, minority carrier electrons at the p side at x equals to minus xp. Similarly, this is minority carrier holes at n side at x equals to plus xn. So now if we have the minority carrier concentration, the total minority carrier concentration, and if we have the equilibrium minority carrier concentration, for continuity equation you remember you need delta n and delta p. This delta n is at the p side and delta p is at the n side. So this is going to be total minus thermal equilibrium. Same for this. Now the total here is what? The total here is electrons at p side, which we saw above, and the thermal equilibrium is electrons, minority carrier electrons at the p side under equilibrium. Similarly, the delta Pn is the excess minority carrier holes at the n side. The reason we are using this delta term because we are talking about the excess carriers, right? So we had the equilibrium minority carriers, we had the total minority carriers, right? We had minority carriers at a given x value, and now we are talking about the excess minority carriers. Excess minority carriers are the total minus what was always present there under equilibrium condition, right? So the excess here becomes the total, which is, let's say, total number of holes in n region minus total number of minority holes in n region under equilibrium condition. Keep in mind that this np is a function of x. This Pn is also a function of x, and therefore the delta Np and delta Pn will also become a function of x. Okay, so if we have understood all of this, and I would suggest that you go through that few more times and memorize these terms, get familiar with these terms, it will help you in subsequent derivations. Now, what is the process to derive transport equation? There is a systematic process. If you just think logically, you will realize that it should be a very systematic process. So what is the process? Let's think from the in a backward term. So in the end, we need a current voltage relationship. We know the current voltage or the current flow in the diode is because of these excess minority carriers which are present in those regions, because the majority carriers in the neighboring region diffused into the other region, right? The diffusion process started because the forward bias was applied. So the built-in potential reduced and it further strengthens the diffusion process. As the diffusion process starts, what you get is you get these excess minority carriers. You get these excess minority carriers, right? And these excess minority carriers, given they would have a certain gradient, right, would contribute to a diffusion kind of a current, right? So if we get this excess minority carrier concentration as a function of x and we apply a diffusion transport equation as we have seen before, we will be able to get the total current, right? The total current will be nothing but the current contributed by the excess electrons or the diffusion of excess electrons and the diffusion of excess holes, the sum of those two, right? Now the question is, how do we get this? How do we get this relation? We don't know anything, right? All we know is we know this, right? And we know the majority carrier concentration, which is N0, and this side P0, and we also know that we are assuming that when these electrons diffuse at this point, the whatever is the majority carrier, the concentration remains the same. So here it has to be an N0, and at this point it has to be PP0. So this is the information that we have. But then from this and this and this and this, how do we get the relation for NPX and PNX? So we studied continuity equation. So we are going to basically find a certain parameters, feed that into continuity equation, and find a relation for these excess minority carriers in these regions. Okay, so let's see our approach, right? First of all, what we'll do, we'll try to basically derive a thermal equilibrium concentration of minority carriers, both the side, using or in terms of the thermal equilibrium concentration of majority carriers and the built-in potential, right? So we have these majority carriers present, and we'll try, and we have this built-in potential in between, and we derived a relation between what happens when these majority carriers diffuse to the other side, how many will be present here, and what happens when these majority carriers diffuse to the other side, how many will be present here. So we'll derive a relation of the number of carriers being present at these edges on the other side in form of built-in potential and the majority carrier concentration, right? Now we'll apply a forward voltage. So the built-in potential is going to reduce from VBI to VBI minus VA, and that is going to disturb the thermal equilibrium concentration. And what we have to find is how much that disturbance is present and what is the gradient of the minority carrier concentration on both sides, right? So that's the gradient I was talking about, right? Now once we derive a relation for the total minority carrier concentration in terms of the thermal equilibrium concentration of minority carriers and the applied forward voltage, right? So you should also remember that the carrier concentration inside the space charge region is constant. However, as it crosses the space charge edge, it will start falling, as I have shown, and this, as it starts falling, it's going to basically give you that gradient. It will fall as a function of x, and eventually at some point it's going to become or converge to the thermal equilibrium concentration of the minority carriers. Okay, so then what we do, then we are going to basically find the total and the equilibrium minority carrier concentration, which we already have from our previous relations, and using that we should be able to find the excess minority carrier electron and hole concentration as a function of x. How do we do that? We have to basically use continuity equation, where the relation for total minority carrier concentration and thermal equilibrium concentration of minority carriers will be used to solve the boundary conditions. There will be a couple of other things that we will use for solving the boundary condition. For example, we will assume that the electric field outside the space charge region is 0. We'll assume that the generation rate is 0, and we'll also assume that this is a steady state situation, means anything which is d by dt will be 0, right? Now using that, we'll have the excess minority carrier concentration in terms of thermal equilibrium concentration of minority carriers, applied forward voltage, and the distance x, right? Now this minority carrier concentration, or whatever I had shown you as going down, right, this as a function of x will be used to find the diffusion current equation or diffusion current density. So we will feed this information into diffusion current equation, and we will find a relation for electron and hole current densities, which in this case is the diffusion current density, as a function of applied forward voltage and as a function of x, and then we find that current density at a particular x and we sum it. That will give us the total current as a function of forward applied voltage for the PN junction diode. Okay, let's do this step by step, and while I'm doing this, make sure that all these bullet points that I had shown in the previous slide are noted down and are there in front of you somewhere, so that you can follow the steps in a very systematic manner. Okay, so now let's start. The step number 1 is we find these parameters that are needed to solve the boundary condition for the continuity equation, right? What are these parameters? The first thing is that we find the minority carrier concentration on the other side of the junction as a function of the applied forward bias or applied bias, and the majority carrier concentration on the other side of the junction, right? So we can start that by built-in potential, that the relation that we derived, right? So the built-in potential we earlier derived as a function of the thermal voltage, which is a constant log of Na Nd by Ni square. Now if we rewrite Ni square divided by Na Nd equals to exponential of minus E Vbi by Kt. Now you know that the Nd here is majority carrier concentration, right? So we can write this as N0, and Ni square by Na is nothing but the minority carrier concentration in the P region, right? So we can write Ni square by Na as Np0, right? Np0 or Np0 is the thermal equilibrium concentration of minority carriers or minority carrier electrons at the P site or the P region, right? So we bring everything back. This was our relation. This is the transformation we can do. The Nd can be written as Nn0, and Ni square by Na can be written as Np0 or Np0, right? Where Nn0 is electrons present at N side, Np0 is electrons present at P side. 0 corresponds to thermal equilibrium situation, right? So Np0 can be written as, right, this becomes Np0, this goes to the other side, becomes Nn0, can be written as Np0 equals to Nn0 exponential minus EVBI by Kt, right? So this relates the minority carrier electrons on the P side to majority carrier electrons on the N side, right? So remember that these electrons which were present at the N side, they start diffusing, and the amount of the number of electrons diffused to the other side at, let's say, this point is a function of the applied or the built-in potential VBI, and will also be a function of how this VBI is modulated with the reverse bias or a forward bias, right? But at present we are considering system is in thermal equilibrium, so there is no minority carrier disturbance, right? So whatever we calculated here, this Np0, the Np0 remains same everywhere, right? Now as we apply certain forward bias, this concentration at the edge would vary, and then it will fall, and at some point it will achieve the same thermal equilibrium concentration. Okay, now let's apply a forward bias and see what happens. So if you apply the forward bias, as I told you earlier, that the barrier which was earlier VBI will be reduced by VBI minus VA, where VA is the forward bias, right? The difference between the quasi-Fermi energy levels is the applied forward bias in this case, right? So what will happen to the electric field? The electric field inside the depletion region will reduce because of that externally applied field. So as the electric field reduces, the earlier, if you remember, that the diffusion process stopped because the diffusion, there was a diffusive force and then there was a built-in electric field, the force because of that, and the point it balances, the diffusion process stops. Now if you reduce the built-in field by this application of this applied forward bias, the diffusion process will continue again, right? And that's what happens in this case. So as you apply a bias, forward bias, the applied electric field is going to oppose the built-in electric field, and therefore the diffusion process will further continue, right, as it started when there was no built-in electric field, the moment you had basically connected these two junctions superficially. So as you, in other words, you can also see that as you apply this forward bias, the barrier between the two conduction bands at the N side and the P side is going to come down, and that is also going to enhance the net flow of carriers from one side to the other side, right? So now if we change our equation, we had this equation here. Now in this equation, if we change VBI by VBI minus VA, what is going to happen? So if we change that, right, we change that by VBI minus VA, what we get is a total electron concentration or excess, total minority carrier concentration or electron concentration at the P side. And if we divide this, if we break this, what we get is Nn naught exponential minus EVBI. This was the thermal equilibrium electrons or electron concentration at the P side. And we get the additional term, which is exponential positive of EVA by KT. So the total electron concentration at the P side, or the minority carrier electron concentration at the P side, becomes a function of the thermal equilibrium minority carrier concentration and the applied forward bias. Okay, similarly we can find a similar relation for the holes at the N side, right? Keep in mind that now the junction is not in thermal equilibrium anymore, right? The forward bias has lowered the potential barrier. The majority carrier electrons are injected into the, from the N side to the P side, and therefore the number of injected electrons are going to be strongly dependent on the effective barrier height, which is VBI minus VA. So as I said, the kind of relation we derived earlier, we can derive the same relation for the holes at the N side. So what do we get? We started with these electron injection, right? These majority carrier electrons were present at the N side, they diffuse. We consider that whatever enters, the same is present at the other point. That's what I said before. But what is that value? The value is denoted by this relation, as we have derived, right? Now the relation, the function that we got, that's actually the value at the edge of the space charge region, the value that enters, the concentration that enters and also exits the space charge region, right? So you can fairly write this Pn as Pn xn, and previously we had this Np. So this Np can be written as Np minus Xp. So we can note here in this figure that Np at minus Xp, which is the starting point of this space charge boundary, right? And this is written in form of the N P naught, which is the minority carrier electrons at the P side under equilibrium, which is this, times exponential of EVA by KT. And a similar relation exists for the other side. So in simple word, if you have a certain minority carrier concentration present under equilibrium condition, the excess minority carrier or the total minority carrier concentration at the edge of the space charge is going to be the thermal equilibrium concentration times exponential of QVA by KT. This Q is nothing but the charge on a single electron with positive sign, right? So that's how we get the electron concentration and the hole concentration at the P side and the N side at the edge of the space charge region, and these concentrations are the minority carrier concentrations when the system is not in thermal equilibrium. So the difference of these two, this and this, or in other words this minus this, will be the excess minority carrier concentration at the p side, and this minus this is going to be excess minority carrier concentration or excess holes at the n side. Okay, so now if we have very clear idea of the minority carrier concentration or different minority carrier concentration at different points, we can actually solve the continuity equation to find a relation for these minority carrier or excess minority carrier electrons and holes as a function of x. How do we do that? We start with the continuity equation. All of you remember this continuity equation, but now we start simplifying. Now what is the simplification? Here delta Pn is the excess minority carrier. So as I said, the difference of these two, the difference of this and this is the excess part. So the delta here denotes the excess part. So the Pn minus Pn naught is the excess part. Excess, in this case we are writing this for holes. So this is excess minority carrier hole concentration. That's the difference between the total minority carrier holes at the n side and the thermal equilibrium minority carrier holes at the n side. Now this, if we solve this, we will get a relation for minority carrier holes at the n side as a function of x. Now for x greater than xn, now xn is the edge where the space charge was terminated at the n side. We know that outside that region electric field is 0, generation is 0, and the system is in a steady state, so anything which is differentiated with time is going to be 0. So this equation translates to something simple, right, which is a second order differential equation. And now this equation is valid for x greater than xn. Similarly, we will also solve another equation for electrons, which will be for x less than minus xp, right. We rearrange this so here the LP square is nothing but the dp times tau p, right. So we got this dp here and we got the tau p here. So the product of this is written as LP square, and if the diode dimensions, for instance, the neutral region, if the neutral region dimensions are called Wn and Wp, and if the Wn and Wp are much smaller than Lp or Ln, then rather using Lp or Ln, you have to use Wp and Wn. In this case, the assumption is that this neutral region length is much greater than the diffusion length Lp. So the same kind of equation that we have written here for the holes at the n side, we can write the same kind of equation for electrons at the p side, right. Now this equation is valid for x less than minus xp, where ln square is dn tau n, and again here we assume that the Wp, which is the length of the neutral p region, is much greater than the diffusion length of these electrons at the p side. Okay, so let's put things together. We got this equation, right, which is the minority carrier holes at the n side at x equals to xn. We got this equation, which is minority carrier electrons at p side at x equals to minus xp. We got the thermal equilibrium hole concentration at n side, and we got thermal equilibrium electron concentration at the n side, right. So this is okay. So now why do we have why basically this, which is a high value at xn, translates to this at x equals to infinity, and why this translates to this? This happens because of the recombination present across the system, recombination with the majority carriers. Now the minority carriers are present in a region where there are many majority carriers, and they are going to recombine with those majority carriers, eventually achieving to these thermal equilibrium concentrations of minority carriers as we go away and away from far and far from the space charge region, right? Now, as I said that we have assumed that these lengths of these neutral regions are very long, right, such that the length of the neutral region is much more greater than the diffusion length, right? Now, this is a case of a long PN junction, and we will see later on that if it is a short PN junction, which means if this is not valid or this is not valid, rather using LP or LN, we are going to use WN and or WP. Okay, so you know that the solution of this kind of second order differential equation can be written as an exponent, right, with a positive exponent and negative exponent, right? Now this is valid for x greater than xn. This equation was valid for x greater than xn, and we have written this excess minority carrier concentration as the total minus the thermal equilibrium concentration, right? Similarly, for the other equation which was valid for x less than equals to minus xp, we can write a similar kind of a solution, and this solution is for excess minority carrier electrons at the p side, which is the difference of the total minority carrier electrons at the p side minus the electrons, the minority carrier electrons, the thermal equilibrium minority carriers electrons at the p side, right? Now, if you apply the boundary conditions as we have given before about the value at x equals to minus infinity and the plus infinity, and x equals to minus xn and minus xp, what we get? We get a equals to c equals to 0, and then we further evaluate for b and d, we eventually get this relation, right? So what is that? What we get is the excess carrier or excess minority carrier holes at the n side is related to excess minority carrier holes at the n side under thermal equilibrium times an exponential function minus 1 times an exponential function which is exponentially decaying with x, right? So this is the reason why it goes like this. So if we go to x equals to 0, what we get is this part becomes a constant and we get a finite value here. Similarly, for x less than minus xp, or for the minority carrier electrons at the p side, we can get a similar relation, right? So if we put these two things together, right, so we got a relation for npx, we got a relation for pnx. All we have to do is we have to feed this into diffusion equation or the diffusion current equation, find the current contributed by these minority carrier electrons at the p side, minority carrier holes at the n side, add them, we got the current voltage relationship. Let's check that. But before that, we why we are adding. We started with these assumptions, and let me remind you about these assumptions. We assume that the total current is constant throughout the PN structure, right, which is this. We assume that the individual electron and hole current are continuous function throughout the PN structure, which means that there is no discontinuity. Whatever happens, they are changing or increasing or decreasing gradually, continuously. And we also assume that the individual electron and hole currents are constant throughout the depletion region. So which means that's the reason why you see this flat kind of a behavior, right? So if we find the current as a function of x, both the currents as a function of x, and if we sum it for any value inside the depletion region, we should be able to get the total current density, right? So we can basically write down the minority carrier hole diffusion current relation, and we can find it for x equals to xn. As I said, we need to add it at any point within the depletion region starting from minus xp to xn, right? So the minority carrier hole diffusion current we can find at the point xn, right? So we feed all those relations that we derived into the diffusion current relation for holes which are present at the n side. right, and we calculate it for x equals to xn. So if you do that and derive, what you get is you get the whole current density as a function of a constant times exponential of E forward voltage divided by kT minus 1. Now this is something which would be looking familiar to you. Now we got the whole current density, right? What about the electron current density? This is the whole current density. Similarly, we can solve it for the electron current density. The electrons at the p side, so we basically find the electron current density at x equals to xp, which is also the edge of the space charge region, and as we said that both are flat inside the space charge region. So if we can find the whole current density at, let's say, this point, and the electron current density at this point, and we assume that it's going to be flat across the entire region, so then we can basically add this and this, which means adding at any of those points, and since we said that adding at any of those points will always result into the total current, which is flat across the device, we get the total current, right? So you basically solve it now for the electron current at the p side, and what we get is the electron current at the p side, a very similar relation, a constant depending on the doping material, other parameters, and an exponent. We sum these two current densities. What we got is the total current density, right? The total current density is function of a constant, we call this as Js, reverse saturation current, and an exponent with an offset of -1. Now here the reverse saturation current is function of diffusivity of electrons and holes, the minority carrier, thermal equilibrium minority carrier holes at the n side and thermal equilibrium minority carrier electrons at the p side, the diffusion length at the p side and the diffusion length at the n side, right? If you plot this relation as a function of VA, so we plot J versus VA, and if you know J, you know that the current is nothing but, if this is the cross section of the device, which is A, the current is nothing but J times A. So you can plot J versus VA, and the same trend will be there for I versus VA, which is J times cross sectional area, right? So you get this familiar relation that you are quite used to of. Now we summarize what we did. We basically found the minority carrier diffusion current densities as a function of distance along the N and the P region, and these minority carrier diffusion current densities, using this we actually calculated the minority carrier diffusion current at a given point. These points were the edge of the space charge regions, and we said that inside the space charge the currents are flat, therefore we can add any value of hole current and electron current as far as they are taken from inside the space charge, and when we add, what we get is the total current. If you plot this relation, which is as a function of x, what you note is at the p side the electron diffusion current would decay, at the n side the hole diffusion current would decay. Now since the total current is constant, we can find the majority carrier electron current at the n side and the majority carrier hole current at the p side, and when you sum these two you always get the total current. Now since finding the majority carrier electron current distribution was tricky, we actually went with calculating the minority carrier electron concentration, and we added this inside the space charge region, and that gave us the total current density, right? Now keep in mind, we assume that the electric field is 0 in the neutral region. But the fact remains that the electric field is not precisely zero in the neutral region. But even if you have a small electric field present, which is the case because of the finite resistivity of that region, so certain potential is going to drop, that small electric field, even if that is orders of magnitude is smaller than the electric field present inside the space charge region, that electric field is good enough for drifting the carriers out from the neutral region, right? And that's the reason why we say that there is a drift component present, which is why one cannot argue that there is no electric field present in that region as well, right? But you can actually find that current that field present by just solving this drift transport equation. You know that drift relation is drift transport or drift current is a function of electric field, so you can find the electric field from the drift current that I have just shown before, and if you calculate that, you will find that the electric field is non-zero but very small, but it's still sufficient for drifting these carriers out. Okay, let's before I conclude, let's see the implications when you make a short device or a small diode, or what happens when you basically change the temperature, right? So when you change the temperature, you remember there were two equations, two terms. You had two terms, one was Js and other is exponential EVA by kT minus 1, right? So Js would have certain dependency on the temperature, and this part should also have certain dependency on the temperature, right? So since Js is inversely proportional to Ni square, and as the temperature increases, Ni square increases. Ni is a strong function of temperature that we have seen earlier. So if you increase temperature, the reverse saturation current is going to increase, which means that this part which is the reverse saturation current is going to increase as you increase temperature, right? So you can actually estimate that the Js will increase by a factor of 4 for every 10 degree centigrade rise in the temperature. Now on the forward side, the temperature is going to have a decremental effect. So if the characteristic is like this, as you increase the temperature, the current is going to drop, right? So you see this, if you increase the temperature, the effective factor inside the exponent is going to reduce, and therefore the current is going to drop. Now as I said, if you have a short diode, and short diode here means that the length of the neutral region, which was Wn or Wp, is smaller than the diffusion length of electrons, minority carrier electrons or holes in those regions, then you have to replace ln or Lp by Wn or Wp in the diode equation, and that will give you the relation for a short diode. Now you should have a homework to find what happens if you make a short diode, whether the current will increase or whether the current will reduce. I would consider this a simple mathematical problem, but there is certain analysis involved, and I would suggest all of you, whoever is watching this video, to go back and find what happens to the reverse current, forward current on resistance of the diode when the diode becomes a short diode, which means that the Wn or the Wp are smaller than Ln or Lp. On this, thank you, and in the next module we will talk about Schottky diode and then subsequently heterostructures and so on. Thank you.